Happy Monday. I believe we should finish up with antiderivatives. First, let's factor out that 3. What do you want to do?
I'm not sure what the rule is called, but there's that natural law that, right? Maybe.
This one's not going to be a natural law. That only works if it's t to the first power in the denominator.
Well, then we set this up as the product of 1 over t or dt over t.
You could, but we don't have a product rule.
Oh, okay.
And ultimately, it'd be easier just to do it this way anyway.
All right.
Look at the last problem we did on Thursday. What did we do there?
T to the minus 2 dt.
Yeah, right. That's a t to the minus 2. Because then you can use power rule, right?
Right.
According to power rule, what is the antiderivative of t to the minus 2?
That would be t to the minus 1 divided by 2 times some constant.
T to the minus 1
Minus 3.
times negative 1. No, wait, divide by
Technically divide by negative 1, but there's no difference. Right, you add 1 to the exponent, and then you divide by that new exponent. So it's t to the n plus 1 over n plus 1. Any of those 3 forms. Right. Antiderivatives, secant squared theta d theta. Well, what function, remember this is what an antiderivative is, what function has derivative secant squared of theta? Tangent of theta plus any constant. Very common confusion. You mix up the antiderivative with the derivative. You say the antiderivative sign is positive cosine. When it's not, it's negative cosine. Or the derivative or the antiderivative of cosine is negative sine, which it's not. The derivative of cosine is negative sine. It's a very common confusion. Happens a lot. So we're looking at sum, so go term by term. It's the second term. What is it? Negative what? Negative cosecant. And then add your constant on at the end. This one's tough. What's the antiderivative of e to the theta?
E to the theta.
Really challenging. This one, let's see who's paying attention. Antiderivative of 3 to the t dt. function is 3 to the t. There's a function.
Would you be able to put it in terms of its derivative and then use the properties of the antiderivatives?
So what do you mean?
So like the derivative of a exponential function, couldn't you do like the ln, whatever its derivative is, and then do what you would do for a regular antiderivative?
Are you trying to use change of variable? You sub? Because you haven't done that yet.
I don't know.
That sounds like what you're trying to do, which we haven't done yet. We can only look at the definition of the antiderivative.
Can we just write this in a different form?
There's no other form you could write it as.
Yeah, we need what would be.
The function's just 3 to the t. There's no simpler way of writing that.
Yes, a lot. No, we don't have stuff we need for that.
You're not incorrect to look at the derivative. What's that derivative?
LGB dx, natural log, times the natural log of b. Which is no natural log there.
Oops, why did I do 3? So then isn't that true? Natural log of b is a constant. Divide both sides by log b. Then scalar multiple rule allows you to pull it inside the derivative.
So we can treat that like an equation.
That's the definition of an antiderivative. B to the x is the derivative of b to the x over log of b. Which means b to the x over log of b is the antiderivative. So there's another known antiderivative.
Do we know the stuff we need to know to find it?
Hmm?
You said there's another known antiderivative.
If that's the known antiderivative. So now we know the antiderivative of b to the x
Oh,
of
I
a
thought-
general exponential.
Oh, I thought there was another example we were supposed to find.
Why does L have to become the denominator again?
Because of this over here. Using the definition of the antiderivative. You know that the derivative of b to the x is b to the x log of b. So divide both sides by log of b. And then use the scalar multiple rule to pull that 1 over log b into the derivative. That is the definition of an antiderivative. How are we going to do this one?
Oh, we don't have product rules, so why don't we just multiply those two things together so we don't.
Yeah, we got to FOIL it. FOIL that out, what do you get?
T to the 5 plus 3t to the third minus 2t to the second minus 6t. The fact that you haven't written that down scares me.
Where'd you get minus 2t to the second?
Where did I get my?
You can do it for
Oh, it should be to the third.
That means that answer's not simplified.
2, 5 plus t to the third minus 6.
Ah, now that's a very simple one that we can take. What's that antiderivative?
T6 over 6 plus T4 over 4. Minus 3t squared. Plus it, plus it, plus it.
So,
I don't like that.
Common denominator?
I want a common denominator. Did you just say 24 and 12 are the same thing?
Kind of.
They're clearly not. 24 is clearly twice as large as 12.
Yeah.
Definitely not the
Still
same.
proportionally similar.
I agree they're proportional.
Close enough.
This isn't government. Close enough doesn't count.
Correct me if I'm wrong, but I believe that would be 4t to the 6 plus 6t to the 4 minus 72t squared, and then all that over 24.
That's not simplified.
Right? Well, yeah, you're not wrong.
2t to the 6 plus 3t to the 4 minus 36t squared.
It's an amazing thing. I'm usually not wrong.
But it looks pretty, it's pretty
No, I just wanted that. This one did make you think a little bit.
Oh, quick question. On whether it's for the sign, for entering an antiderivative, do we have to do a capital C or a lowercase c?
That's a good question. It should tell you in the instructions.
Alright.
Or it may just give you with the plus, or it may just give you plus C, and you just have to put in the simple part.
E to the pi times x plus c.
Yep, that's all it is. Yeah, e to the pi is a constant.
Yeah, what's the first 5 numbers of that? Okay. Four shot.
So now something that's going to come up quite a bit in applications, especially physics. The idea of initial value problem. Or an IVP. An initial value problem is a problem that involves solving a differential equation given a specific condition. In this case, we have the very simple differential equation, f prime equals sine of x, with the condition that f of 0 has to be 2. You'll study more advanced differential equations and differential equations.
Are we supposed to just find the antiderivative but throw in the right constant to get our constraint over there?
If f prime is sine of x, that means f is the antiderivative of sine, which is what?
Negative cosine plus a constant.
Plug in 0. What's cosine of 0? F of 0 is negative 1 plus c. That has to equal 2. What's c? There's the solution to this initial value problem. F of x is 3 minus cosine of x. So an initial value problem gives you a single solution. Because now it has to satisfy a specific condition, which means you're only going to get one value for c. First, solve the differential equation. So what's f of x? Next, the initial value. In this case, it's not really an initial value. And we just apply the condition. They still call it an initial value problem, even though we're not using quote-unquote initial. Now, you typically think of initial as 0. What is tangent pi over 4? And the solution to this initial value problem is tangent of x plus 4. Second order initial value problem. Once you start to get up to higher orders, there are two types of problems you can encounter. Initial value, or what's known as a boundary value problem. Notice f prime and f are both at the same value pi. That is how you know it's an initial value problem. Boundary value problems are typically more difficult to solve. Way more difficult. I don't think you've really studied boundary value problems until partial differential equations. Which is not actually a requirement for any major level. However, my two physics people may want to consider taking it. Because a lot of the problems you deal with are partial differential equations. And yes, you do encounter boundary value problems in physics, specifically quantum mechanics. Start by finding f prime. F prime would just be the antiderivative of f double prime, right? What's that antiderivative?
C.
We can call it C1 in this case. You have a choice. You can find C1 now or find it later. You could. In fact, for some more complicated ones, you may have to. It's not going to matter. You can do it now. What is cosine of pi?
Negative.
What's C1 then? F prime is 1 minus cosine of theta. That means F is the antiderivative of that. What is that antiderivative? X? It's not X.
Well, you don't have it in the order you want it in, but that'd be sine of theta plus theta. No, negative sine of theta plus theta. And
It's set. It's theta, not X.
And then plus C2.
That is another common mistake. Using the wrong independent variable. Tells you what the independent variable is. It's d theta. So you better make sure everything's in thetas. What is sine of pi?
Zero.
What's C2? There's the solution to this initial value problem. Theta minus sine theta plus 4 minus pi. So key takeaways. Anti-differentiation is the process of undoing a derivative. Unlike when finding a derivative, finding an antiderivative gives you an infinite number of solutions. A family of solutions is what it's called. Your antiderivative is unique up to a constant. So the only difference is going to be by a constant. So you cannot forget to add that constant of integration, as it's called. Without some starting value, without some known condition, you cannot find C. If a condition is given to you, you can then find that C. And that is an initial value problem.
About those order value problems you mentioned earlier.
We're not going to deal with those in this course.
Okay.
They'll be discussed in differential equations if you have to go up that high, but I don't think you really even solve boundary value problems in that course. That's more of a partial differential equations topic, which I know you don't have to take because it's not a requirement for any major. Not even math, it's an elective for math. Now actually, my two physics people, if you go the route of taking mathematical physics, I think partial differential equations is covered in that course. I think you do touch on it in that course because that's supposed to cover all the math you need for the upper level physics courses. So you may actually do it if you decide to go that route, but you don't have to. There's two paths you can take. There's the math physical route, and then there's the take linear algebra and differential equations route.
Did you say that class was ordinary differential equations?
It's called ordinary. The title is ordinary differential equations, but it's just titled. It's just referred to as differential equations.
But the mathematical methods for physics class is that linear algebra and ordinary differential equations.
And I think it also covers some more advanced topics as well,
All of them.
because they don't go over everything. They don't really delve into the theory. They just introduce what you need for physics from those courses. Right, so you don't, the bulk of linear algebra, you don't actually need in physics. You probably only need like 3 or 4 weeks of linear algebra for physics. The rest of it you don't use. So right there, that takes away how many weeks? And again, for differential equations, you're going to need a bit more of it, but you don't need the whole thing. Again, I don't know what that course actually entails, but I would assume they're going to teach you some PDE in it. I would assume they also teach you some stat. Because you need stat for physics. So who knows, you may see it, you may not.
Well, isn't proofs a prerequisite for physics? So how do they teach you that?
It shouldn't. It shouldn't be. Again, maybe the curriculum changed. I can't remember. Maybe it is now, I don't know. But again, that's because in mathematical methods for physics, they don't do the theory. They don't really delve into the theory of everything. So they just kind of tell you, here's how you solve the problem, without actually deriving why that's why we do it. And so I can tell you for ODE, they would just give you, okay, here's the differential equation of this form, here's its solution. Without getting into why is that the actual solution. They just tell you, here it is. Another key takeaway, even though we haven't seen it, unlike with derivatives, antiderivatives are a lot harder. And the vast majority of the functions do not have an antiderivative, right? Here is a key example. E to the negative x squared over 2 dx has a derivative. Does not have an antiderivative.
So not even just, we can't calculate it, it just doesn't.
No, there is no analytic antiderivative. There's no, I don't want to say analytic. There's no antiderivative. Now, if I do this, that can be solved using numerical techniques. Right? Because there's still an area under that curve. In fact, that is a very common function. That's called the error function, actually. If I do this, that's the error function, RF of t.
And the t is supposed to be distinct from x.
Yeah.
Okay.
So it's written this way. This function is also a very common function. Who said stat?
I can recall a friend who took it.
Who's taken a stat course? Wow, I thought they forced that in high school now.
No, it was not. I love it.
So do you recognize this?
You know, I don't remember much. It was good class, but
This is the standard normal probability distribution.
So that gives us a normal distribution,
Standard normal.
standard normal. Different from normal.
Yes.
Okay.
Well, it's not different. It's a special type of normal.
Okay.
Standard normal is the normal distribution that has mean of 0 and standard deviation of 1.
Okay.
Versus the normal distribution can have any mean and any standard deviation.
Okay.
Right? But that function looks a lot worse.
I don't like those.
That's the normal distribution.
I liked it better before.
But you work a lot with that function in stats. And it has no antiderivative. But guess what the probability is? An integral. So you're going to be, so you deal with numerical techniques a lot in stat. So neither of those two functions have an antiderivative. But they're very common functions.
All right. Nice feeling by being the first one to prove that there could be an antiderivative.
Good luck.
Okay.
Because there is none.
All right.
What function, when you take its derivative, gives you that? None exists.
Nice. Yeah. Okay.
But you'll get more into those types of integrals in Calc 2. I'm just simply introducing it that integration is a lot harder, which is why we introduce it in Calc 1 and you spend half of Calc 2 doing it. Because it's that difficult. I feel like there should be more homeworks, but
If you want, we can find your info. I didn't all the way